Hello and welcome to the 5th lecture on human-like artificial agents. Today we will focus on spatial awareness and discuss the background of environment abstraction we are using during the labs for some time already. So far we have been discussing decision-making in previous lectures. Today we are moving to the reasoning part of the IVA. So what is spatial awareness? It is the capacity to understand, reason and remember the spatial relations among objects or space or oneself. It is quite large part both within the psychology and neurobiology, who are looking into how we as humans process spatial information. It is having different names, like ability or intelligence, which differs in a point of view but discuss similar things. What is crucial for us is that spatial awareness is closely linked with perception and reasoning, as it is something we think about and decide then upon. So look at this grim-looking virtual world. How do you perceive it? What spatial information is this picture giving you? There are some kind of towers, one lit in blue, one in red, so perhaps some kind of fortresses. There are ledges, and it seems you can fall off into the void, and drawing onto our experience is probably something to avoid. The top of the tower seems like a great sniping spot, as there you can see a whole exterior of the map from. Wait, not everything can be seen, someone can hide behind the tower. But the tower is steep looking. If there is possibility to get on top of the tower, it probably leads through the tower, so the tower probably has some interior hidden from the top of towers as well. But the towers are connected only by this bridge in the middle. So, if those are really fortresses, then the sniping spot would really be a valuable place, as we can guard the access to our fortress from there. And the map looks symmetric, so if I get to know the interior of my tower, I might be able to navigate in the other. Wait, why am I calling the red tower mine? Am I in the red team, meaning that blue painted avatars are my enemies? So is this arena of some team-oriented duel? So you can see that we have not decided on anything, but we have reasoned about the environment a lot already, just from this one picture. And it is natural for us humans to reason like that, as the virtual environments are mimicking the real world we are used to. So that was human reasoning, which is giving us a good notion of what spatial reasoning in IVAS will be. In a nutshell, any data structure or code that deals with the reasoning about the environment can be labeled as something contributing to spatial awareness of IVAS. Every time you will be writing a code answering what items are around me, or how do I get to some concrete item, or what are the safe routes leading from my base to the enemy base, what is a good ambush spot, or how to actually dodge a rocket, you will be writing spatial awareness code. So what are the, let's say, spatial features we will need to be dealing with the most? We are talking about physical properties of the world, important for safe navigation, so floors, walls, pits, obstacles. Objects that we may need to interact with while navigating through the environment. Items that may interact with the space like rockets or mines, thus changing the perception of safe spaces, for instance. But also about dynamic objects, and not only rockets but also other IVAS, which are in relations with the space and other objects. So what kind of techniques are connecting with dealing with those spatial features? To represent the space, we will need some kind of environment abstraction, and we will need some navigation code for that. Interactive objects will require annotations. As we are not in robotics, we do not have to recognize objects. But we will certainly need to have a way to interact with those objects, and for that we use theory of affordances, through which we can distribute some part of IVA intelligence onto the environment itself. With respect to objects that are associated with some mechanics, we will require some kind of forward model, that is, a notion how those objects behave in time and on what they are reacting. And for dynamic objects, we will need some code how to navigate around. Or in case of cooperation, how to coordinate IVAS. Out of these topics, we will be covering environment abstraction and representation of visibility, as these are the foundation to many spatial reasoning routines. So first, environment abstraction. How does virtual world are actually being created? As graphics cards are crunching triangles the most, the list of triangles represented by vertex and index lists is always an option, but there are other ways as well. For large outdoor environments, representing the terrain with triangles would not be efficient. Instead, we can have a large matrix of heights that can be turned into triangles easily. The downside of this technique is that it does not allow you to represent caves or overhangs. For some objects, it might be beneficial to represent them through the means of constructive solid geometry, where the target object is constructed out of the primitive shapes via set operations like union, intersect, or minus. Actually, Unreal Engine 2 was using this representation for the environment inside its editor. However, it's been dropped in next versions, as it does not make sense outside of ray tracers much. It is beneficial to work with triangles directly. Even though one might need a lot of triangles to represent fine details of models, there are ways how to combat them during rendering, like use of tessellатors, but that is outside of the scope of our lecture. This is that the environment is a soup of triangles oriented in 3D space. And there can be quite a lot of them. If we take a few example maps from UT 2004, we find that number of triangles are ranging from tens to hundreds of thousands. Now, representing the map as merely an array or a list of triangles does not make sense, as the simple question of finding the nearest triangle to my position would require us to query all of them. Luckily, similar questions must be answered during rendering as well. One of the frequently used techniques for storing spatial data like triangles are BSP trees. We exemplify the idea inside 2D. Let's say we want to quickly answer a question: what are the points around my position? Typically a question that seems to be of O(n) complexity with respect to the number of points. However, if we create a BSP tree, we can make it O log n. The idea is to recursively divide the space with lines in 2D or planes in 3D until some terminating condition is met. Here the condition is that each region contains one point at most. Such a tree can be then used to easily locate a region where you are standing and thus find points which are nearby. That's how it might look in 3D. Triangles belonging to the same tree leaf are rendered with the same color here. When building such BSP trees, the question always is what kind of lines or planes to choose for the separation. In 3D, one possibility is to use axis-aligned planes. Their advantage is that it is easy to check on what side your point is. From the information of the plane type, that is XY, XZ or YZ plane, it takes just one comparison to decide whether you are on the left or right of the plane. This leads to partitioning the space into rectangular cuboids. Additionally, you can compute what other cuboids one in question share its faces with. Such an information is then making it easy to raycast such a structure. That is, answering a question, can I see point X from the point Z? Here is the example from the UT and Pogamut itself. The visualization is slowed down intentionally so you can see a bit how the ray is cast. As you can see, the ray is traveling through cuboids, checking whether it does not collide with triangles, which are associated with them until it hits something or we reach its destination. Now, this raycasting is quite powerful. Technically, it provides you with the way to answer if there is anything that would block some segment cast from point X towards point Y, which can already be used for answering question whether there is a line of sight between points, or is it safe to fire the rocket along this line. And if you can toss a lot of those rays, you can find out whether some point is actually a good sniping point as well. But there are limitations to what we can use raycasting for. First, it's just a line, but we usually need to question a volume, like a rocket cannot be replaced with a point. Theoretically, we could use multiple raycasts to mitigate that, but it will always be only an estimation. The same goes for holes or pits. It is hard to build a notion how big or large is a hole next to you. Answering that would require tens to 100 raycasts, and unfortunately that is not feasible if you aim to support, for instance, 100 of IVAS. Finally, raycasting won't help us with pathfinding much. Before we get to pathfinding, allow me one detour. If you need to answer volumetric raycast, you can do this using physics engines, where you can ask the engine to cast a sphere along some line, checking whether it hits something along the way. But back to pathfinding. Using BSP-tree for pathfinding is no good, as it just confines triangles in subspaces. We need proximity information, that is, how triangles connect to each other, or in better terms, what triangles are linked through the actions of movement and jumping. What if we use triangles directly? As they are typically represented with vertex and index lists, we get the proximity directly out of that. But well, it depends. Some maps are huge, so considering all triangles in there, the pathfinding algorithm might run quite long. Additionally, not all triangles are suitable for movement like walls or ceilings, if you are not actually an alien. This leads to the idea of abstracting the environment for the purpose of navigation. These abstractions can be categorized along the dimension axis between 1D, 2D, and 3D techniques, namely navigation graphs, navigation meshes, and voxel navigation. So let's start with the most simple one, the navigation graphs. So the idea of navigation graph is to place a navigation point onto the place where one bot can stand collision-free. Originally, those points were placed by designers manually. Then people start using automated navpoint placing. As you can see, if we see the environment through the prism of points, we lose a lot of semantic information like position of walls and pits. But if we connect those points with links where each link is something a bot can traverse collision-free, we receive an abstraction that is directly usable for pathfinding. It constrains us to travel between points only, but if we cover the floor with enough points, we will receive a graph that is dense enough in order for the navigation of bots to become believable. Of course, it will be the crude abstraction still, so it won't help us dodge incoming rockets, as we could easily fall off the ledge we do not know about. Automatic placement of links might not be perfect, so we must watch out for potential collisions along the way still. There might be also misplaced points, so not all of them might be connected within the graph. And if designer fails to place enough points, we could easily be surprised by someone from behind. Luckily, we can annotate the points and links with more information, which could give us additional spatial information or gameplay information, like this is a good place for a sniping point, or this is a place where a rocket launcher is being respawned, or this is a point you need to guard if you want to prevent enemies entering your fortress. This is a teleport that leads somewhere, and so on. Additionally to those kind of information, we might even provide the sense for the floor that is around particular points or links. For instance, we can associate each link with a distance, how far you can astray from it and still remain safe, thus covering the floor with rectangles like this. Or we can associate such a distance with each point to cover the floor with circles. And if we do it carefully, we can treat the area between circles along the links as walkable as well, which is actually a very efficient representation considering how much space it allows us to cover with respect to the amount of information required for the representation. Manual placing of navigation points is of course tedious, but with the help of OpenCV we can automate the process. Let's consider this 2D case. That is, an image we can receive from orthogonal projection of triangles representing walls, which we can label according to their angle to the floor. If you know at least one pixel that represents free space, you can fluid fill this to find walkable areas. Then you can extract contours. Mark the walkable areas with fluid fill, and then use Delaunay triangulation with holes to get triangles. Clip those outside of walkable areas, and generate a dual graph from the triangles, that is, placing a navigation point in every triangle off the center. However, simply connecting centroids is no good, as two triangles sharing an edge may form non-convex polygon. Thus, a link connecting centroids goes through an area outside the triangles, like here and here. The solution is to add more points into the graph, like centers of triangle edges or the corners. Here we have an example where we have added points into all corners of the contour. If we do this, then result paths are not bad, as corners of contours are typically bending points of the shortest path leading to our target. So, what are the pros and cons of this navigation abstraction? With respect to the size of navigation graphs, quite good. However, take those numbers with a bit of salt, as those graphs were manually created. We can treat them more as a lower bound. Automatic navigation placement would yield much higher counts, roughly 2 to 4 times, but still quite low number with respect to the triangles. Another pro is that we can automate their placing. Designers are also given tools to associate the nodes and links with extra spatial and gameplay information. However, the result movement looks quite mechanic, as the navigation goes over the same links again and again. So let's switch to 2D abstraction called navigation mesh. The idea of navigation mesh is to cover the floor with convex polygons. Convex polygons have desirable property that a segment that connects any two polygon points lies within the polygon itself. Therefore, it is easy for a bot to navigate inside a polygon. However, polygons alone cannot represent all navigation opportunities connected, for instance, with jumping. In that case, we combine the navigation mesh with so-called off-mesh links. Typically, off-mesh link requires a specific type of path-following code in order to reach the other target. For instance, another off-mesh link may be a lift link that requires the bot to use the lift in order to reach the other end. Another example may be a teleport link. Navmesh can be computed automatically out of the polygon soup. Since around 2009, there is commercially usable implementation called Recast. The Recast algorithm is quite technical. It splits the space into voxels of arbitrary length, removes those that the bot cannot stand in, and then it constructs the polygons of the navmesh out of what was left, stitching the floor of voxels together. There is a lot of parameters associated with the process, like the highest possible step of an agent, maximum slope an agent can stand on, and so on. Interestingly, this algorithm is being used today and can be found both in Unity and Unreal Engine 4, for instance. So, how good is this abstraction? Looking at the navmesh polygon count, we see it is roughly 10 times higher than the number of navigation points, but it covers all the areas where the bot can stand. Plus, the navmesh is quite good for casting the rays through the navmesh. We can create navmesh automatically. Additionally, we can throw arbitrary triangle soup into the recast and it will try to do its best. Unfortunately, pathfinding is not that straightforward as in navigation graphs, as we will see in a minute. As we have the floor covered, it allows us to use safe steering techniques, which will make sure the bot won't really bump into the geometry. Moreover, steering techniques using navmesh raycasting are cheaper than traditional raycasts. Just remember that polygons must be combined with off-mesh links still. Now let's talk a bit about pathfinding within the navmesh, as finding a path is the main use case for it. In the pictures we see the same environment. On the left we have the environment abstracted using navigation graph, and on the right with navigation mesh. If we want to find a path in the navigation graph abstraction, we just fire A* algorithm and the result will be our path, that is, A star will return us a list of navigation points to travel through in order to reach our target. But how to find the path within the navmesh? The idea, of course, is to use polygons as nodes that are connected with polygons they share a side with. The problem is how to decide on the distances between polygons, because that depends on the final path that is unknown. We have two options here. Either abstract each polygon with its centroid as pictured on the left, or abstract each side with a middle point as pictured on the right. Using polygon centroids, we receive graph that is of the same number of navmesh polygons, whereas using side middle points yields us a bigger graph. But also higher precision. If we consider the final path as pictured by green dotted line, we can see that the right abstraction is better. Nevertheless, it is an estimation, and what is worse, it overestimates the distance or the length of the final path, and as an effect, finding a list of polygons to navigate through might not yield us the shortest path always. Consider this case where we want to find a path between two green dots. The shortest path is quite obvious. However, the polygon path before refinement is going to be quite different. We can fight this by trying to split polygons until they are roughly of the same area, so these weird cases won't happen. Finally, having a polygon path is not enough for path-following algorithms, as we need to have a list of points to navigate between, as in the case of navigation graph. So how to actually extract that, as using, for instance, centroids is no good, and using middle points of polygon sides is not optimal. The answer is a funnel algorithm. The funnel algorithm is constructing the path by identifying the bending points. It maintains the current funnel, and then it moves the funnel as it walks over the sides of polygons we have to cross. Once it discovers that the funnel is too narrow, or should the two funnel segments cross, it labels the point responsible for that as the bending point of the path and restarts the funnel algorithm from that point. Even though the theory is simple, the actual implementation needs to discuss quite a few edge cases, but nothing fatal. So let's see how navigating using navigation graph and navmesh looks like. This is shooted from the Unreal Tournament 2004. You can see the depiction of triangles which are forming the environment. These are the triangles we are making the navmesh from. And here is the example of the navigation. We already computed the navmesh, and you can see the bot navigating through the environment. You can see that the bot is able to use the off-mesh links, and it is walking along the optimal paths. You can see that the shortest path is typically bending around the corners of the navmesh. This is a bit unbelievable. Typically, when you are using this kind of navigation, you also combine it with steerings, which keeps you a bit off from the walls. Here you have an example of link riding. But all in all, the navigation using navmesh is pretty believable. Let's see now how the navigation using navigation graph is working. Here you have the navigation graph visualized. You can see that the number of navigation points is quite low. That's because the game comes from 2003. So we had just Pentium 2 back then with 300 or 400 megahertz. So you have to save computational resources as much as possible. And the result movement looks a bit mechanic. Sometimes the bot even collides with properties of the environment, and some navigation points are really misplaced. But we will reach our target nevertheless. And now for the same navigation request, but now using the navigation mesh abstraction. The path is even a bit different. And it is using the whole floor for the navigation. The result movement looks much more natural. Sometimes traversing and off-mesh links is having a problem because they are taken from the original navigation graph. But we do not see that the bot would be bumping to the geometry as previously, and we can see that it can finish the path faster. Having the abstraction of the environment for navigation is nice, but it still is missing the information about visibility, which is crucial for many spatial tasks like identifying sniping points, ambushing enemies, fleeing from them, or finding a cover path. One visibility query can be answered by raycasting. But if you are trying to find a cover path hidden from some sniping point, you would need a lot of those raycasts, which is not feasible. As raycasting is slow, we again need some kind of abstraction that is pre-computed during the design time. One such an abstraction is visibility matrix. You cover the navmesh with points, and by using raycasting, you pre-compute Boolean matrix according to the raycast result between those points. Anytime you want to query the visibility between 2 points, you find the nearest points you have sampled via PSP and check the matrix. Moreover, if you store the lines of the matrix as Boolean vectors, it opens the door for interesting reasoning. For instance, if you face multiple enemies, by computing the inverse of logical ORs of lines where the enemies are located, you will receive the set of points neither of your enemies can see right now, so you can avoid them. Or if you actually want to engage with them, you can find a point from which you can engage just with one of them. Let's say we have chosen our target here. Here are the points our target is visible from. These are the points other enemies can see. And so we can combine it to find points we can shoot our target from, but which are hidden from the other enemies. That's all for today. Thanks for listening. Next time we will be talking about steerings that will allow us to smooth the path following and avoid other dynamic objects. And as usual, if you have questions, feel free to email me. See you and take care.